Today we're going to start chapter 4, section 4.1, graphing polynomial functions. This entire chapter is going to be dealing with polynomial functions, solving them, working with them, applications thereof, things of that nature. A little bit of key vocabulary first of all. First one, number one, the degree of a polynomial. So a polynomial is something that has many terms with it, like a monomial, binomial, trinomial, etc. Could have many terms, but the degree would be the highest exponent that you see in the polynomial. So remember that. Number two, just a reminder, f of x. That is the same exact thing as y. It's just reserved for function notation. F of x, g of x, h of x, etc. They all mean y. And finally, number three, those two values, I know you've seen them before, positive infinity and negative infinity. And what those imply would be ideas that there's got to be some largest number that exists and some smallest number that exists. Let's go down and talk about what polynomial functions could look like and then how to describe what's called end behavior. All of what we are discussing is intended to give you more understanding about a polynomial function, which then allows you to have a greater ability to work with it, solving it, doing applications with it, operations involving it. So let's start looking at an example of a graph of a polynomial function, for example. So in this case, we have this graph, and what I've got up here is it says describe what's called the end behavior of the graph of this polynomial function. So to do this, we need to analyze this graph carefully. But before we do, let's consider a couple things. Now, I think we're all in agreement. This is the x-axis. The vertical axis is the y-axis. But in this case, since we're dealing with function notation, we could call it f of x. It's the same thing as y, isn't it? Now, in addition to that, let's look at the values that are on the x-axis. As you move to the right from 0, 2, 4, 6, 8, etc., if you were to continue going on the x-axis to the right, you would approach what's called positive infinity. Conversely, if you move to the left of the origin, -2, -4, -6, etc., you would reach eventually the concept of negative infinity. Now, we don't really know what those numbers are. It's just an idea that numbers will keep going. Likewise, for the y-axis or the f of x axis, as you move up, you will eventually reach positive infinity. And as you move down, you will eventually reach negative infinity. So let's keep those concepts in mind as we do this. To describe what is called end behavior, we need to read this graph. And over the years, you should have learned that the way you read a graph is from left to right, just like you read a sentence in a book. So let's pretend that we have a point on the graph. I'll put one right here. And the idea is that let's analyze the path of this point as it moves along this curve. And what we want to describe is its overall tendencies. And that's called end behavior. When you understand the end behavior of polynomial functions, it makes it very easy to predict what they may look like. And then when you begin to analyze those graphs for specific purposes, you'll have much better chance of being able to do so. So let's take a look at this point as it travels. So I want everybody to think about the x-axis and think about the fact that this point contains an x and a y value, doesn't it? So as we move along this graph, actually, let me lock this thing in place. So as we move along this graph, let's say that we are a point and we're going to move toward, on the x-axis, toward positive infinity. So if I'm over here, I want everybody to understand, as I move along the curve to the right, the x values are getting bigger and bigger and bigger, aren't they? Because I'm moving to the right. So my question is this: what are happening to the y values eventually as I move to the right? I know they're going up and down right now, but what are they eventually going to approach? Let's do that one more time. So here I am. I'm going to move left to right. So as the x coordinates of this point are getting larger and larger, my x values are, because I'm going to the right, what's happening to the y coordinates eventually? Can you imagine what would happen if I kept tracing along this graph? Would you agree with me that it would keep going down and down and down forever as you move to the right? Eventually it would, wouldn't it? So that is one description of end behavior. So I'm going to write this on the graph, and I want you to go ahead and do so as well. So I'm going to say that I think the y coordinates for this graph are going to go down eventually toward negative infinity as the x coordinates go to the right on the graph or move towards positive infinity. Now, likewise, what if I trace backwards on this graph? What do you think happens to the y coordinates as we move toward negative infinity? So let's go backwards on this. So I think we're all in agreement, I think we should be, that as I start moving to the left on this graph, the x coordinates, they have to start to get smaller, right? Like this point right here has got smaller and smaller x coordinates. That point right there has got an x coordinate of 0. So what's going to eventually happen as I move farther and farther and farther to the left? What will happen to the y coordinates or the f of x coordinates? Aren't they going down toward negative infinity as well? They're getting smaller and smaller and smaller. They sure are. So I'm going to say that the y coordinates are going to move toward negative infinity as the x coordinates move toward negative infinity. And these two statements together are a description of the end behavior of this graph. Might be a little difficult to understand that at first. Now look at the shape of that graph. I want to show you something else. What's the degree of this polynomial? It's 4, isn't it? And isn't 4 an even number? All right, yes it is. Let's go to this chart down here. Okay, I want everybody to look at this. This is a chart for end behavior. The top two sections of the chart deal with degrees that are odd. Let's not even look at those right now. Let's look at the bottom of the chart. Even degrees. And then the next thing I see is it says leading coefficient, if it's positive or negative. Well, doesn't our graph that we just did, doesn't it look like it's got an even degree? Was the leading coefficient negative? Because the graph kind of looks like that picture. Let's go up here. What's the lead coefficient, the first coefficient that you see? It is a negative number. So we're starting to learn something about polynomial graphs. And here's a summary for you. So if you have a degree that's even and its leading coefficient is negative, it should have a general shape something like this. Maybe not specifically, but more importantly, this is the end behavior. This is what we wrote down up there. We said that as a point moves to the right, the y coordinates went downward. And as a point moves to the left, the y coordinates also went downward. That will be true for every polynomial function that's even with a leading coefficient that's negative. Now, conversely, let's look at the other side over here. What if we still had an even degree polynomial, but the lead coefficient was positive instead? It would simply be turned upside down, reflected the other way. Now you think back to when we graphed quadratics. Didn't that happen? Yes, it did. We said if the lead coefficient was positive, it opened up, negative, it opened down. It's the same idea. And that's how you can express your end behavior for that. All right, let's move along to another example. It'll start making more sense as you go through this. All right, so I want everybody to graph that in Desmos. And let's see if we can describe its end behavior. I'll give you a moment to graph it. All right, so after you're done graphing, I went ahead and took the liberty of doing a graph. And this is what my graph looks like right here. And this is what yours should look like as well if you typed it into Desmos correctly. Now, before we get into that, let's go back up to this equation. Let's see if we can dissect this a little bit. All right, everybody, think about this. What is the degree of that graph, first of all? Okay, so what I should have heard from somebody is the degree is the highest exponent. It's 3. So that means that we, in this chart, are only going to be focusing on these 2 possibilities for end behavior. Those are degrees that are odd. Now, everybody look at the lead coefficient. What's the lead coefficient of this graph? All right, I see it's positive 2.25, right? It's positive. So that means that what we are going to focus on would be this particular situation. So what you would write down for this situation would be the following. This is the first statement that you would write down. Actually, the order does not matter. So what this says is, and I'll demonstrate with a point like we did on the last graph. Pretend that you're a point on the graph. Go all the way to the left like I've done. Now what I want you to do is move that point to the right and look to see where does it eventually end up. So as I move this point to the right, you can see I go up, I go down, but eventually I'm going to go up, 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 and never stop. So what I've highlighted over here would make sense. Let's talk about this and highlight it. My y coordinates are eventually going toward positive infinity. They are going up as this point moved to the right according to the x-axis. Now everybody, let's reverse that. What happens to this point as it moves toward the left on the x-axis? So everybody, x-axis goes left and right, right? Let's go start moving this point to the left. So I'm decreasing, increasing for a short time, and then I'm going to be decreasing from then on. So what does that mean? Well, my y coordinates now are decreasing toward negative infinity as I moved to the left, as x approaches negative infinity. And I want you to be able to use that notation. Now, keep in mind, the chart to the right of this describes what would have happened if the degree was odd, but the lead coefficient was negative. It would be completely reversed because your graph would look something like this. This is a chart you're going to have to memorize until it makes sense to you. And what you got to get past is the notation of how to write these things. Let's try another one for practice. How about everybody graphs that in Desmos and makes a sketch for yourself? Here's what my sketch looks like. Can we describe that end behavior? Okay? Without having a chart in front of us. First thing everybody should do is discover what is the degree. Everybody get your degree and get your sign of your lead coefficient and see if you can write the correct end behavior. See, eventually what we want to be able to do is write this end behavior without looking at a graph. You should be able to just look at an equation and make that determination. Pretty hard to do at first, but eventually you'll be able to do that. All right, so the degree of this is 3. That makes it an odd function. Now, if you haven't picked up on this yet, odd functions are going to start and stop in different locations according to the y-axis. Even functions start and stop in the same location according to the y-axis. The lead coefficient happens to be negative. So for someone like myself who's used to doing this, that means a lot to me. So for you, eventually, hopefully this will sink in and you'll get the idea. Now, if you need to, look back at your chart to see if that helps you. But what I could do is I could make a prediction about this without even looking at the graph. Okay, without even looking at the graph. So I'm going to predict that the y coordinates are going to approach negative infinity as the x values get larger and approach positive infinity. And I'm going to also say that the y coordinates are going to approach positive infinity, or in other words, they're going to get larger and larger and larger as the x values get smaller or they approach negative infinity. You go ahead and look in your chart. That's going to match up with what we have written. Now let's go ahead and prove it by looking at the graph. So what we do is get a point on the graph all the way to the left, as far as you can get. And what we're going to do is we're going to scan all the way to the right. So what I'm going to do is this. I'm going to do that part right there, everybody. I'm going to move this point so the x coordinates increase or get larger. Okay, so I'm watching, I see it's decreasing. Now it's going to increase. Now it's going to change directions again, it's going to decrease. But if I keep going to the right, do you see what's happening? You see how the y coordinates are getting smaller and smaller and smaller forever? That's the description for that. The y coordinates are getting smaller. Is it starting to make sense now a little bit? It takes a while to get through this. Conversely, now I'm going to do that movement, everyone. I'm going to take this point now and I'm going to move it to the left. I'm going to let the x values, coordinates get smaller and smaller. So look what I'm doing. I'm increasing, but wait a minute, I'm changing directions, decreasing. Now I'm increasing again, and I think I'm going to keep increasing forever, which is this. The y coordinates will increase forever. So odd degrees, see how it starts and stops according to the y-axis in different locations? That's what happens with an odd degree function. Evens, they start and stop in the same location. I'll try to summarize that here at the end in a second. Well, everybody tries that one. All right, I've got the graph provided. Well, let's say you didn't have the graph. It'd be pretty hard to do right in the beginning. We're trying to understand this. But use them both in conjunction to see if it makes sense to you. So first thing I would do is I would try to classify this function, even versus odd. You look at its degree. Okay, that is an even number, right? This is an even function. So to me, that means it'd be kind of like a quadratic function, something like that. The y values are going to start and stop in the same area. And I can see on the graph that they do. The lead coefficient is a +1, which means this thing should open up, and it does. Once again, I'll summarize this in just a moment to try to help you make sense of it. So now I want to write the end behavior. Well, let's do it this way this time. Let's see if this helps you out. All right, so first thing we're going to do, let's move that particle to the right, and let's see what happens to the y coordinates. Okay, here we go. So as I go to the right, I start falling, then I rise, then the point falls, then it rises, and as I keep going to the right on the graph, looks like I'm going to keep going up, 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 and I'm never going to stop. Let's write that. So the y coordinates are eventually going to keep rising. They're going to go to positive infinity as the x coordinates were moving to the right to positive infinity. Let's try it the other way. What happens if we move to the left on this graph? All right, so as I move to the left, I begin to fall. Then the point begins to rise again. And it falls again. Then it rises, and it's going to keep going up there because it's going to finish in the same place with respect to the y-axis because it's even. So these y coordinates are going to positive infinity even when x is moving to the left. That's because it's an even function. So let's try to summarize this, make some sense of it. There is your assignment. Let's get some reference here. Let's draw a little sample. That's what y equals x plus 4 might look like. Now, do you guys notice that this is an odd function? Lead coefficient is positive. You look at your chart, you see how this function starts and stops in different areas according to the y-axis? Now, that's an odd function, right? And all odd functions behave that way. How about an even function? How about something simply like y equals x squared? We studied those. Looks like that, right? See how it's an even number? It's an even function. Lead coefficient is also positive. You see how those y values are both ending up going toward positive infinity? So even functions will go in the same direction, odd will go in opposite directions. Now, had I turned these lead coefficients to negative, these graphs would simply flip over. One last thing. When you deal with higher degree polynomials, you might not see a line. Maybe it might be something more like this instead. See? Or maybe this one might look something like this. You don't know, but eventually they take on a similar shape. All right, you go ahead and give that homework a try.